want to talk to you today about observability at the long tail. And kind of, so we talk about observability, we deal with really large data, and so we inevitably take some techniques to kind of reduce the complication of that data. But that can really hurt our ability to kind of understand the 95th percentile or the 99th percentile of our data. And so I want to talk about some popular techniques that people use, and we can talk about when they work, when they don't work, and then I'll introduce you to kind of a large swath of research that comes out of the databases and the theoretical computer science community that really thinks about this in kind of streaming use cases, the kind of use cases that we have in lots of production systems. All right, so I am here on behalf of WhyLabs. We're on this mission to kind of build an interface between human operators and AI applications. We have a SaaS product that does kind of AI observability and monitoring. But what I really want to talk about today is a thing that we're really proud of, and a thing that really is the core of even our SaaS product, is WhyLogs. So this is an open source library. It's really about kind of pulling the right telemetry from your machine learning data. And we'll talk about why it's so special and kind of how efficient it is and all of the algorithmic work that kind of goes into making this efficient as we kind of ponder the case of the long tail and rare events. Okay, I'm happy to see this moving. So production data is often has high volume. It's dynamic. You have more and more data coming in, and increasingly in this kind of streaming form. It's coming in continuously, and the sorts of techniques that you might have from any machine learning or statistics training may not work here because we're used to maybe batch data or static data. We're holding it in memory. We're doing this processing. And there's certainly, ways to do that or to kind of distribute your work and use the same sort of algorithms. But I think increasingly, production machine learning systems and those who operate them will think about the complexities of scale, if they haven't already, and then the streaming data. And one thing is, if not only thinking about the stream, but we also have rare events. So if you have dynamic data like this, the work it takes to kind of analyze these data points and figure out which of these data points are outliers or record information about these particular data points can be quite interesting. So to grapple just handling the scale of data at all, there's a number of techniques that people use. So one, many practitioners use some sort of simple sampling techniques. So if you have, you may retain kind of the full data set for special use cases, but there's lots of companies and practitioners who just can't retain every bit of data that happens, so they'll keep some sample. Maybe it's a 1% sample, maybe more, depending on the size of the data that they have and their interest in retaining it. And most use a very simple sampling technique, just a random sample of 1% of the data that comes through. Others kind of move into the space of slicing your data into segments, different ways to segment and slice your data, largely based on time if we're thinking about this, this kind of streaming use case, but then also other characteristics. So here I think I have the different colors representing some helpful characteristic. You might split it into, let's say, cities. Let's say we have some product that may operate differently. Your data may look differently by city. You may want to split it in that way, in addition to splitting by time. And when you split that, there's some analysis you can do on these different sections. And so we'll talk about what people are often doing But I would characterize anytime that you're looking at a data set and trying to understand characteristics and maybe even then store those characteristics as profiling that data. Okay, so the rest of this talk, well, there's kind of two parts. This first part is going to be about comparing three techniques, which I think are the kind of certainly the first two are the fundamental ones that people look to when they're trying to analyze streaming data or just large amounts of data for the first time. The third one I will try to do my best to convince you is a more efficient one and kind of gives you benefits from both sides. So we're going to do this in the context of kind of median and quantile calculations. So what's the 50th percentile? What's the 95th percentile? What's the 0.1 percentile? All right, so the first is static metrics on subsets of data. So after we've split this data into the number of windows that we have, we may simply kind of collect a dictionary of important metrics that we've determined ahead of time that we want to calculate on it. So means, medians, maybe a certain number of quantiles, min, max, if you have output data, if this is attached to a model and this is inference, you may have performance metrics, things like that. The next is, so this is just storing those metrics, and you may store some subset of the data as well, but as far as kind of where you do your analysis, you're just kind of basing it on those metrics that you've stored. The second one is random sampling. And there's a number of sampling techniques, and so I admit that I think for a more thorough analysis, I would kind of go into the details of different types of sampling, but here I'm just going to keep it strictly random, and this is kind of what I see a lot of people using. So just storing some random sample of the data for further analysis. You store it in a database, things like that. And so what that means is that when I want to go back and do some analysis on my data, I'm pulling that info down or running this inside of my database on the raw data in the same kind of form. And finally, I'll say data profiling for streaming data. So while the collecting static metrics can also be data profiling, I want to really talk about kind of particular data structures and algorithms to collect more detailed information about data as it's streaming that can better summarize the data and comes with error bounds and can handle these kind of rare events better. Okay, so let's get to an example of the first one. The first one is capturing these simple preselected metrics for machine learning data. So some benefits is that once you've collected, let's say, some metrics like this that I'm showing to the left, it's really fast to do analysis on this. So you have a list of metrics, you can pull them up. I think there's a number of different tools that allow you to kind of store metrics in this sort of form. I see it in kind of feature stores. I see it sometimes in kind of experiment management tools, things like that. It's really convenient to now go back and search across all of these because it's just a small dictionary often. Because it's a small dictionary, it also has low storage size. So this can be really beneficial relative to the large amount of data and storage that you may need if you're storing actual data. This is quite small. Actually, it's quite small by any standard. And another benefit that you won't see for the others is that these metrics that you calculate, at least with respect to the subset that you've determined, are exact. So once I calculate this, I'm using a standard kind of algorithm to calculate mean, median, and these sorts of things. You likely have exact values. So some cons. One con is that you have to determine these metrics ahead of time. So if you haven't picked any metrics or there's some metrics that you want to include later, perhaps they're kind of business KPIs or other metrics that you want to use for your model, you can't go back and recalculate them just based on this approach alone. You'd have to have stored that data or stored a sample of that data to try to estimate it. And lastly, I will talk a lot about this in a little bit, but it's non-mergeable, and mergeability is going to be really important for a number of things, for kind of your ability to have flexible analysis later, and the lack of mergeability will really, really make it difficult for you to understand anything about the tail of your data in aggregate. Yeah?
But I see that you have measurements for like one variable, but we could think of this as like different combinations of variables, you know, like the covariance in there or something like that.
Yeah, I think that would still fit if you have multiple variables. Yeah, I think this whole thing is pretty much kind of univariate that I'm doing this on, but no reason to be other than simplicity. Okay, so here's a number of questions that you would want to answer, but you can't really answer depending on the metrics that you chose for a static approach. So does the estimated value of a new metric that I've come up with, what does that look like on prior data, right? We can't get that. When I start to think about maybe new things like overlap of this data with some set of important values, relative rank of this value on last year's data, so if this is some sort of aggregation, the drift between two data sets, so something like this, if you look to the right, you have kind of the first part of the KS statistic, which is a popular way to measure distribution drift. And so what you need there are two CDFs, and you need basically the maximum distance between the two CDFs, and you take that and you find a statistic on it, Kolmogorof's, and then you can get some sense of whether or not these things are drift or just statistical error, perhaps. And so this is the thing you couldn't calculate, really, if you're collecting pre-selected metrics in this way. And then error bounds, so kind of more complex ways of thinking about the error that would result from this, and many more. And a large reason for some of the problems with this approach is that it lacks the ability to merge the data together. For one thing, if you have a stream of data, you likely don't even have fixed bins, and so that makes mergeability hard on its own. But even so, your ability to merge multiple of these pre-selected kind of sets of static metrics can really, really hurt your ability to do this rare long tail analysis. So I'm going to go over random sampling a bit, and then we can dig into kind of more of the deep analysis stuff here. So I'm just going to turn this a little bit. So random sampling of machine learning data has issues as well. So on the left, it's formatted a little differently, but it's just a kind of the first couple rows of a CSV, just to highlight that like you do have data in the same form that of your original data, and that is one of the first benefits because your data scientists know how to interact with this data. They probably already have scripts to interact with this data in this form, and that can be highly beneficial. It's also highly flexible, so even if it is a random sample and it has some problems on outliers that we'll talk about in a bit, it allows you to calculate any metric later that you want, and that can be really beneficial. It can work for batch or streaming data, depending on, sometimes people get into trouble if they try to pick a fixed number of data points as opposed to a percentage, because in that case you need to do something like reservoir sampling. It's just a little more complicated on getting kind of an equally distributed sample if you have a fixed amount, but it does work on streaming data or batch, and it's mergeable. There's rows in a cell, so you could add a new column, have a date, and merge them however you'd like. Some issues with this is that we'll talk about in a bit with some experiments, kind of poor estimates on the tail and outliers, and poor precision, depending on the percentage of the data that you are taking as a sample. And then high storage size. This is just full data, especially if you're calculating some simple metrics in the future, may not be worth it. Okay, So what is this third option that I'm sort of proposing? Well, it fits into the umbrella of data profiling, as I mentioned. And so data profiling is really just the act of reviewing and analyzing a data set to understand the structure and information. Often what comes out of it is kind of a collection of descriptive statistics, similar to what we saw in the first option. And normally there's lots of kind of detection things. So you might detect the data types, patterns, data structures. You may have like outlier detection. A lot of other models have data quality examinations, so something like grade expectations or the equivalent. But these data profiling techniques can get more advanced, and that's what we do over at WhyLabs and what I want to talk about today. So these are some things that we either have or are kind of actively developing inside of this data profiling process. And this includes things like error bounds. So we do have error bounds on all of the estimates that we have, which are really, I think, important. We also have things like feature importance. You can include feature importance. We're starting to include outlier detection, so as a process during the streaming profiling process. And a number of things. You can create like a surrogate model to go on top of your data and so on. Okay, so this is what I'm going to focus on and what we do at WhyLabs, and what I think is really an approach that helps you at the tail for rare events. So this is sketch-based data profiling. And so we'll talk a bit about data sketches, but essentially they are a number of algorithms to create very efficient data structures that can look at the data only once, so in a kind of streaming form or online format. And there's a number of things that we can collect. Some benefits to the sketching-based data profiling are you still have fast access to key metrics, similar to the kind of static data profiles. You have high flexibility, maybe not the same flexibility that you have with raw data, but you do have high flexibility. It's very low in memory and storage size. Unlike the kind of static metrics, it is mergeable, and that's really key to understanding rare events. It's built on kind of a large academic literature, which I think is great, and something that is important to reuse. So databases underneath the hood, most databases these days use sketches because there's a lot of cases where you can get away with kind of approximate subsets and things like that, as opposed to kind of the exact count. Some cons. So there's some pre-selection that happens. These sketches kind of involve complex algorithms underneath the hood, and so translating those algorithms to a particular metric may take a little bit of work, or at least deciding that you want to include that into your profile. Okay, so we learned all of this. I don't think any of us knew this at the time about these data sketches and sketching techniques when we were setting out to build kind of a standard for profiling machine learning data. So we also started with those static data, those static metrics, but we really wanted these 5 properties: lightweight, which you can certainly get; configurable, which is fine; mergeability is a key component. So streaming, being able to work on streaming data, and something that's statistically sound. So we thought, well, if we collect metrics and then we do some weighted average across them, that doesn't really tell us kind of what the bounds are for our estimates, or when we can tell, we can only estimate them at a pretty not exciting level, very, very wide bounds. And so this is largely, our tools are largely powered by Apache Data Sketches, which is an open source data sketching library. All right, now for math. I'm sorry that I made you guys wait 28 minutes until the math. So now let's talk about how median and quantiles work. And we'll start in the box to the right. Actually, no, let's start to the left, and then we'll do the example to the right here. So for a stream of numbers, so we're getting a stream of numbers, x1, x2, so on and so forth, with the current stream length n. So n's going to continue to tick up, increment every time we get a new data point. And for a stream, in the streaming setting, we have no idea when the stream's going to stop. We can't say how many data points we're going to eventually see. This is going to harm us in a little bit, but that's okay. So some notation for rank and quantile, because I find that even I got them backwards sometimes until I had to write it down in this way. So a rank of X tells you kind of a sorted list or of a list, how many of the elements just in count are less than the value, have a value less than this X. Relative rank, which is sometimes used just for the word rank, or is just normalized by the number of elements that you saw, so between 0 and 1. Quantile, what it tells you is the value such that the rank of some data is equal to this quantile, or sorry, I should say the relative rank is equal to this quantile. So for example, let's look at the right. If I have values in a stream 5, 4, 1, 5, 6, 2, the first thing that we would do if we were trying to calculate a median is sort them. So we sort them 1, 2, 4, 5, 5, 6. And then we can say, well, the rank of the number 4 is 3, because there are 3 elements that are 2 that are less than and 1 including itself, so that's 3. The relative rank is just 3 out of 6. Although I guess it depends on when we ask for these ranks, but I'm assuming at the end of these 6 data points that I've given you. And then the quantile, so the quantile at 0.5 is the number 4. Or someone say 4.5, it kind of depends on how you're defining that there when you're split. But we're going to go with 4, so there's kind of a less than or greater than approach to thinking about quantiles, and we're going to go with the less than approach here. All right, so rapidly increasing in the math here. Let's talk about exact calculations of this on streaming data. So, I mean, calculating a median isn't that bad. We've all done it. Take some data, sort it, find out how many are in front of it. But it gets much harder if you think about it in a streaming setting, because so Monroe-Patterson actually proved that it takes into the 1 over p amounts of data points that you have to hold in memory to find the exact median or any quantile. So for example, if we wanted to do this in one pass, if we only see the data once, it's coming in and so we only see the data once, then p is 1. And so we need to hold in data points. We need to hold every single data point to get the exact median. Because otherwise we won't know, right? In the worst case scenario, you see 5 data points. You say, okay, there's no way I'm going to need either of these 2 n's. And then you get a bunch of zeros, right? And so now you needed all of those numbers at the end. So you have to hold all of these. And the way that calculating quantiles work kind of underneath the hood for anything that you've run in memory is they take multiple passes to do this, right? So you can kind of filter this down. And now that we filter it down, we know kind of the max and min, and we can continue to filter down until we get to the middle quantile. So this takes quite a bit of space if you're trying to do this in one pass. But approximate calculations are where you will want to go if you're trying to calculate anything quantile related for streaming data. And data sketching techniques allow us to do this. So there are numerous algorithms. I won't go into these, but I will say just looking at the space requirements for a single quantile, so 1 over epsilon log of log squared, 1 over epsilon delta, or sorry, 1 over, I have those flipped, 1 over delta. And then if I want to do this for all quantiles, right, because we don't want to just calculate the median. We want to know, again, what's the 99th quantile, what's the 99.98th quantile, all of those things. Then it's multiplied from that. Okay, so I won't go through this in detail, but I just want to give a kind of an appreciation for how these kind of algorithms work to approximate the quantiles. So largely, it's just really simplified sampling combined with some numbers that you keep track of so you can understand the error and give better estimates about quantiles that you dropped or don't have in your set. So if you see the top row, there's 7 elements added, and those kind of dotted lines going down are queries that we're going to make in a little bit later. So the way that this works is kind of a compaction technique. Basically, you have a buffer. You might take in 6 data points, and then once you have those 6 data points, you will drop a number of data points and keep track of how many you've dropped or like the number of compactions that you've done. And so you'll see this kind of 2 number come up here. And then you might do that again or multiple times to get even more compact. And this is how the file size gets so small that you're able to do these multiple compactions and still kind of maintain a good estimate as long as we're keeping track of some information about the number of compactions and the nature of those compactions. All right. So I'm going to maybe step back out for a bit before we jump into the experiments and just talk about profiling and when you would do this sort of sketch-based profiling. So we find that we do it both on kind of training data or static data sets. And in this case, it's mostly to just reduce the file size and have kind of a format in which we can collect all of these interesting metrics without reanalyzing the data very often on our kind of large training set. Although that's normally pretty doable. Training data is normally large enough. You have a machine large enough to process it, of course, because you've trained a model on it. So the big use case is profiling ongoing production data, where we're creating these batches maybe once per hour, once per 5 minutes, once per day. And the cool thing about having these is, so if I separate these out one by day in this picture, in the next month, I may decide, okay, well, last month's data, I don't need that granular. I'm going to reduce and merge together each week to save some space. And I can do that so on and so forth. So I can have data from 5 years ago that maybe is at the monthly level, despite me collecting it at the daily or 5-minute level in real time. And that's a huge benefit of the mergeability. So we're going to kind of look at a single profile. So there's lots of cool things that you can do with multiple, starting to think about kind of drift detection and these sorts of things and monitoring. But we're just focused at the single profile now. And I want to talk about specifically data sampling versus profiling and comparing the error at the tail. So we finally got there. And so this is a bit of the experimental procedure, just random sampling a number of data records. We're taking the subset of records based off of what percentage we've set, comparing that exact value, so for things like the median or the 95th percentile, running it a total of 24 times and averaging those results. Okay, so we're going to do it on a number of distributions. Some distributions are probably very familiar to you: normal distribution, uniform distribution, discretized normal, and uniform, so discrete values, categorical data sort of style. But I'm going to add one more in here, which is the Lomax or the Pareto type 2 distribution. So this has a bit of a fat tail. The traditional Pareto distribution kind of has its peak at 1. But this, the Pareto type 2 or the Lomax starts at, starts at 0 typically. And I think Pareto, you can give a parameter for where it's going to be. But this is what it looks like. It's a little hard to tell that the tail is fat unless you look at normal distributions a lot, but it's a much fatter tail than you might see on a lot of other distributions. Okay, so here's some experiments. So this is in blue, are the kind of results from doing this sketch-based profiling. And in orange are the results from sampling. And the longer the bar, the worse it is, because this is error. So for median, if we want to take our data, which I think was 100,000 samples, and calculate the median using kind of a sample of this, and then comparing it to the actual median on the true data, you see kind of pretty large error. It's relative, but so 0.1 for normal distribution, so on and so forth. So for Pareto and uniform, I have these in relative error, which is probably easier here. So 0.1 for sampling and a little under half of that for profiling. Yeah?
So we should be thinking about the profiling method and the sampling method as using kind of equivalent storage costs here.
Yes, I did. Did I detail this on here?
You said that already.
So yeah, I think I skipped over it as far as saying it, but it's number 2 on here. So what I did is I subset some number of records that's equivalent to the number of bytes of the profile. No, that's okay. I don't think I read it either. I skipped the big paragraphs. That's why I don't have an exact number for the sample, because there's some fixed costs for the profile size, and I wanted to match those. And so now we start to see the 95th percentile, and we see some larger differences here. And looking at the tail is really difficult. And one reason is this, even for sketching. So we can kind of get low rank error. So this is some results from a much newer sketching technique for Quantiles. And ping mesh is the name of a Microsoft server data set. But we can get quite low rank error. So typically you think of error in kind of how many ranks was I off by. But when you think about value error, if you're looking at a long tail, these might be really large values or really small values. This thing increases a lot. So even if it's a low percentage change, that blows up when you're in kind of the tail end of your distributions. And the cool thing about using sketches is that you can kind of customize how you want to treat error across rank. And this is, I think, where the magic comes in. So on the left, we have kind of our default setting for the sketch. We kind of say we want to treat error kind of evenly, absolute error evenly across all of the possible ranks. So even on the long end of the tail, the long tails, and in the middle. The only place that you'll see it's really low is right at each end, and that's because the sketching techniques do keep track of the actual min and the actual max. But then you can also think about customizing this. So let's say the rare events that I'm going to run into, or the real issues that we have, the real cost, comes when the rank is high or when the values are really high on my distribution. So I might have an application where if I encounter a really, really high loan amount, having errors for this is more problematic than somewhere else. And so we might want to reduce the error that we expect here for the high end of the ranks, and then leave the other end alone. Or customize this based on kind of the needs of your particular application. Any question on this? Otherwise, I'll go forward and kind of wrap up here. Oh, yeah, absolutely. So this, maybe I'll come back to... Oh, I guess this isn't a great picture for it, so I'll just sketch out the intuition a bit. But essentially, what happens is that you're keeping track of a certain kind of small list of numbers, and then a number of metrics. So this kind of weight metric for different points in the list of numbers and the samples that you have. And so because you only need those weights, you can essentially you can lay these two samples on top of each other and describe kind of in rank terms, so between the, like, let's say 0 to 25th or 25 percentile, this is how much I need to adjust the values when I give a query. So, like, essentially, all we're doing is we're defining a sample, and we're defining between a fixed interval, between 0 and 1, how much you need to adjust the values for. Because they're all in this this fixed interval, it means that you can easily stack them on top of each other and come out with a new adjustment factor that accounts for both. All right. So I'll go forward and then we can finish with questions. So yeah, if you want to try this, you can there's really cool ways we can extend this and have this information, use this information for metrics, kind of statistical tests, those sorts of things. And yeah, I'll just go to the question slide and finish off with any questions that you guys have.